Okay. So now you can hear me. Okay. So the topic here is supposed to be string theory from a worldsheet viewpoint. And my last paper that had anything to do with that was published a number of years ago. And I think it's somewhat interesting, but I prefer to speak about more recent work, and the organizers said that would be okay. And I've noticed that others have also deviated from the worldsheet, so I don't feel too bad about it. So there have been interesting developments in recent years for constructing tree amplitudes for four-dimensional supersymmetric theories, and I wanted to learn about them, and I collaborated with Kangha Wen, who you heard earlier today, and with one of my students, Matt Heidemann, and we've been working on this for over a year, and I would like to report what we did in our 3 papers. There is lots of work by other people, which I won't take the time to reference, but the references are in our papers. So I'm going to mention 5 theories in 6 dimensions. The first one has 2-0 supersymmetry. So just to remind you of the notation, that means that there are 2 left-handed supersymmetry charges, each with 8 components, so that's 16 supersymmetries. And so that's a chiral theory, which is associated with a world volume of an M5 brane embedded in an 11-dimensional Minkowski spacetime. And the second theory I'll talk about is associated to a D5 brane embedded in 10-dimensional Minkowski spacetime, which is in a 2B context, and that has 1,1 world supersymmetry, so also has 16 supercharges. And the third theory with 16 supercharges is maximally supersymmetric Yang-Mills theory in 6 dimensions. Then I'll talk about maximal supergravity in 6 dimensions. And finally, I'll talk about chiral supergravity, 2-0 supergravity, coupled to tensor multiplets in 6 dimensions. Some of this will be very sketchy because there isn't time to go into a lot of detail. The number of particles involved in on-shell amplitudes is even for any of the Born-Infeld-like theories. And the first 2 theories on this list, the M5 brane and the D5 brane, are Born-Infeld-like, so they only have non-vanishing amplitudes when an even number of particles participate. The other 3 theories also have amplitudes with odd number of particles, but in the last case, there needs to be an even number of tensor particles. Okay, so the first thing we had to do, which had been pretty much done by others before us, is to understand the spinor helicity formalism in 6 dimensions. So the massless little group in 6 dimensions is spin 4, which is the same thing as SU2 times SU2. And so an on-shell 6 momentum for a massless particle can be written in terms of variables called lambda by the equations shown here, where the indices capital A and B take 4 values labeling a Lorentz spinor in 6 dimensions. The matrix PAB is antisymmetric, so it has 6 independent components, as it should. And the indices little a and little b refer to the little group, the first SU2 factor in the little group. And so those indices just take 2 values, which you can call plus and minus if you like. And so this is the formula for the momentum. And this describes a massless thing, which is obvious because this matrix only has rank 2, so its determinant vanishes. And it's the Foffian, which is the square root of the determinant, is proportional to p squared and vanishes. Okay. However, there was this other SU2 in the little group, so that there's an alternative definition you can give for the momentum using the second factor in the little group. And in this case, it's convenient to use subscripts capital A and capital B for the Lorentz spinor coordinates. And so this is an alternative form of the momentum vector that has the analogous properties based on the second factor in the little group. But these two formulas are not independent. They're related by the equation here. And so the lambda tildes are actually determined by the lambdas, aside from SU2 transformations, which are irrelevant to this equation. So let's turn to the M5 brane. So let's first talk about the supermultiplet that we're dealing with here. So it's what's called a tensor multiplet, and it consists of a self-dual tensor, spinors and scalars. And so I've listed these fields here. So the R symmetry of this theory is spin 5 or a USP4, and this can be thought of as arising from rotations of the 5 dimensions transverse to the M5 brane embedded in an 11-dimensional Minkowski spacetime. So the 16 on-shell degrees of freedom for this tensor multiplet are given by the formulas here, where so the notation is that the first two numbers refer to the little group. So we have a triplet of the first SU2 and a singlet of the second SU2. And then the third number is the representation of the R symmetry. So this is a R symmetry singlet, a 4 and a 5. And so altogether you can see that there are 8 bosons and 8 fermions here. And this will be an interacting theory of this tensor multiplet. It's in a sense an abelian theory. It's like Born-Infeld, except instead of having a U1 vector gauge field, it has the self-dual tensor, but it has the same kind of structure. In fact, if you dimensionally reduce this theory down to 5 dimensions, you get a standard supersymmetric Born-Infeld theory. So this theory has 16 supercharges, and in the spinor helicity formalism, one can write them as follows. You have these 16 charges here. So the A is the 4 of the Lorentz spinor. I is the 4 of the R symmetry. So that's 16 supercharges. And then we've written them then with fermionic objects eta here. So we have 8. So we have 8 fermionic objects eta. These have these commutation rules, and then when we put that together, you can immediately see that Q anti-commuted with Q gives P, like it should. And this omega over here is just the metric of the symplectic group. So the 10 R charges in this notation are given by this formula. So what's convenient to do is to pick out 8 of these 16 etas, to pick out 4 of the 8 etas, I was thinking ahead, that anti-commute and then treat them as Grassmann numbers. And so that's what we're going to do. And there are different choices of how to do that. One can either choose half of the I, restrict the range of I to half of its values, or else restrict the values of A to half of its values, and those will be anti-commuting. And so you have to sacrifice either the manifest R symmetry or the manifest world little groups symmetry when you make this choice. And we found that it's more convenient to sacrifice the R symmetry. So what we're going to do is pick out just 8 of these etas by restricting the index capital I to run over the first 2 values. And that's what we'll do. So the full R symmetry won't be manifest. However, one can make it manifest at the end by making an appropriate Grassmann Fourier transform on our formulas, and then the R symmetry becomes manifest. So one can, in that way, one will be able to verify that it's actually being implemented. So that's what we're going to do. So in the basis where the symplectic metric has these values just in these particular off-diagonal locations, then we have our 8 anti-commuting Grassmann numbers when we restrict I and j to be 1 and 2. So in this notation, the 16 supercharges decompose into 8 supercharges that are mutually anti-commuting, and then 8 more which are also mutually anti-commuting, and then these with these are the ones that whose anti-commutators are non-zero in the obvious way. So in this basis for the etas, the entire supermultiplet can be encoded in just an arbitrary function of eta, which can be expanded out in the way sketched here. And so as I said, only an SU2 subgroup of the R symmetry is manifest in this way of writing it. So first I'm describing the multiplets, and then I'll tell you about the theories. So the multiplets that will be relevant for the D5 brane and the Yang-Mills theory are 1-1 vector supermultiplets. So I want to describe what they look like. And in this case, there are 4 directions transverse to the brane in the D5 case. And so you're dealing with spin 4 or SU2 times SU2 R symmetry. So in this particular case, the R symmetry group and the little group happen to be the same. That's just an accident. So in the same kind of notation as before, we have the vector field transforms the 2, 2 with respect to the little group, whereas the 4 scalars transform as 2, 2 with respect to the R symmetry group, and so forth. So these are the fields that make these vector multiplets. And the 16 supercharges can then be assembled as shown here. And again, there are certain etas that have non-zero anti-commutators. So again, we're going to restrict the R symmetry index to just take the value 1. So here the I and j are running from 1 to 2 because we're dealing with the let me say it more carefully. So we have 2 SU2s for the R symmetry. So when we have an index I, that refers to the first SU2, and the I hat refers to the second SU2 in the R symmetry. And we're going to restrict both of those indices just to be 1 on the etas when we want to have anti-commuting Grassmann numbers. So doing that, we can drop since the I now and the I hat only take 1 value, we can just drop it and call those Grassmann numbers eta and eta tilde as shown. So we have 4 etas, namely 2 etas and 2 eta tildes, and again just writing a multiplet just as an arbitrary function of these etas. You have an expansion like that which incorporates the entire supermultiplet. So now let me turn to the supergravity multiplet. So this has 2, 2 supersymmetry, so twice as much as the previous theories. And you can imagine constructing it either by tensoring the constructions I've shown before, either as 2, 0 times 0, 2, or 1, 1 times 1, 1. And the latter choice turns out to be preferable because in the 2, 0 M5 brane theory that I'll discuss, we only have amplitudes with an even number of particles, whereas in the 1, 1 theories we also have the Yang-Mills where there's an odd number of particles, and so the 1, 1 times 1, 1 construction, it will be more convenient. So anyway, this theory has USP4 times USP4 R symmetry. And the multiplet, again using the same kind of notation, the supergravity multiplet. So here's the graviton. It's 3, 3 of the little group. So a graviton in 6 dimensions has 9 polarizations. And and so on and so forth. And here are the 25 scalars, which form the coset of SO5 comma 5 divided by US times SO5 times SO5. And this supermultiplet then can be written, again, as a function of the etas and eta tildes by the same methodology I've discussed previously. So just to show you how useful this formalism is, I've written down the 4-point amplitudes, the answers for the 4-point amplitudes of all of these theories, or for 4 of the 5 theories that I'll talk about. So the 4-point amplitudes, so remember we have, in each case, we've set it up such that half of the supercharges are mutually anticommuting. And so these delta functions make those supersymmetries manifest for these amplitudes. So these delta functions, like this one, are just the statement that those 8 supercharges are conserved in the amplitude. To see that the other 8 supercharges are conserved, one does the Grassmann Fourier transform I mentioned, which makes the R symmetry manifest. And then by commuting the R symmetry with these supersymmetries, you generate the other supersymmetries. And so you prove that those are implemented as well in that way. So, three of these 4 theories have total symmetry in the 4 particles, the M5, the D5, and the supergravity. Whereas the super Yang-Mills just has cyclic symmetry, and then you have to multiply by a color factor and add cyclically inequivalent permutations. The S and T's here just show you the poles that you expect. You see, these don't have any poles because there are no 3-point functions, right? Because these only have an even number of particles in the amplitudes. So these formulas are very concise because they encode an enormous amount of information if you think about it. It shows all of the entire 4 particles for the entire multiplet, the interactions. So you really couldn't imagine having simpler formulas than that. Okay, so as I've already said, the super Yang-Mills formula only has cyclic symmetry, needs to be multiplied by a color factor in a standard way and summed over. Yes. So the D5 is an abelian theory. You would just have a single vector supermultiplet that's self-interacting by a Born-Infeld type of theory. So it's a supersymmetric extension of Born-Infeld in 6 dimensions with just a U1 theory. For anythings in the multiplet. It includes the entire supermultiplet. So by reading off the coefficients of the etas, you can pick out any particles you want from those formulas.
So there should be some order of alpha prime in front of that.
I'm not doing string theory here. I like to do string theory. I've done it in the past.
You have a parameter, dimensional parameter in this body.
Yes, you're right. And those amplitudes, I didn't say it in words, but I said up to constant coefficients. Okay, and momentum conservation delta functions. Okay. So let's turn to amplitudes now. Pardon? Where did those amplitudes come from? Well, I'm going to show you the endpoint amplitudes now. So there are special cases of what I gave you that as an advertisement. I didn't explain it, where it came from. And now I'm going to show you how we get the end particle amplitudes. Okay? And they'll be the special case. So we're going to use this Cachazo et al. Formalism, or the CHY formalism, in which we associate a coordinate on the Riemann sphere to each of the particles. So the index I runs from 1 to n, where n is the number of particles that we're going to consider. And these positions are defined up to a common SL2C transformation, the usual kind of story. So the n-particle tree-level amplitude for the M5 theory has the structure indicated here. So let me explain it. So I'm going to tell you what the script A means. It's not the usual thing, but I will explain how it's related to the usual thing a little bit later. There's a certain measure, which is basically the CHY measure. Then there are two factors. One, which is all the Born-Infeld type theories have this kind of factor, Dirac-Born-Infeld. And then there's another factor which has to do with the supersymmetry. And since this is a theory with 2-0 supersymmetry, we have the appropriate factor for that. So I have to tell you now what these things are. So each of these I factors is required to transform under the SL2C with weight -2 in order that the entire formula has the appropriate SL2C invariance. The CHY measure transforms with weight 4, and if each of those factors has weight -2, then it'll add up to 0. So this is the usual thing where the SL2C maps every sigma simultaneously by an SL2C nonlinear transformation of the usual sort. And then what we're saying when I say it has weight -2, it just means that this I transforms in this way when you do that. Now the construction, which is some kind of inspired by the twister string work of the past. We don't drive things by thinking about twister strings, but from that work we know that it is convenient to introduce polynomials in a coordinate sigma, and so we have a whole bunch of bosonic coordinates and a whole bunch of fermionic coordinates that are the coefficients in these polynomials. So the CHY measure is sketched here. I'm not going to discuss it very carefully. So it involves integrating over all the bosonic objects, the sigmas and these rows which are in those polynomials. And then you have to divide out various volume factors to account for the symmetries that we're dealing with. There's an SL2C that acts on these rows as well as the SL2C that acts on the sigmas. This Vn is some Vandermonde kind of thing down here. And then the most important factor is this delta B. B stands for bosonic, and which is made out of the rows. So it says that it forces the momenta to be identified with evaluating these polynomials at the point sigma I, and then constructing this object in the way shown, and dividing by this factor. So that's the formula for the measure. So that'll be common to all of these theories. So those delta functions imply the famous Chy scattering equations, and we've seen them before in this week, or yesterday, I should say. And so the Chy scattering equations, which go back long before Chy, but anyway, I'll credit them with it, are that when you sum this thing over J, understanding that Pi dot, when I is equal to J, that's 0. And it looks like 0 over 0, but it's 0. Those are the scattering equations. And there are it's hard to see in your head, but you can show that there are consequences of those delta functions in the measure. So and these scattering equations as has been mentioned previously, are n minus 3 linearly independent equations for the sigmas that are defined up to an overall SL2C and have n minus 3 factorial solutions, which you don't need to know. So the left factor is very simple. It's the one that goes in all Born-Infeld-like theories. And it just uses the same matrix that appeared in the scattering equations. And its determinant is 0 because this only has rank n minus 2. So you have to you put in this prime, which means crossing out rows and columns P and Q, and then multiplying by this factor to fix up the SL2C transformation rule. And so in this way you can define a Pfaffian or a determinant, whichever you like. And I've shown you both. Okay, so that's the IDBI factor. And then the second factor was the I20 factor, which has to do with the 2-0 supersymmetry. So all the integrations here are over Grassmann coordinates. The bosonic integrations are all in the thing already in the CHY measure, and these are just Grassmann integrations. And so we integrate over all these parameter coefficients that we had in the Grassmann polynomial earlier. And we have the same van der Waals determinant factor. And then we have something analogous to what we had in the previous slide which related the momenta to certain objects. And here we're relating the 8 commuting supercharges to the analogous quantities. And then this thing will then transform with weight minus 2 again as required. And this is the formula that we found works. So the logic is as follows. I told you that this script AN is not quite the usual thing. This is the usual thing. So this object includes delta functions that tell you that these momenta are massless, that the particles are massless. So we don't normally write those down in front of an amplitude. So we want to pull them out. And then there's some other peculiar looking delta functions which you wouldn't normally write down. And so the logic is that the fact that once you know that you have these delta functions, then you're allowed to write P in this form. And once you know you have these delta functions, then you're allowed to write Q in this form. And in that way, you introduce the lambdas and etas into this expression here. So then once you've done that, you can throw all this garbage away, and here's your answer. And so the analogous procedure for the other theories. So I told you now the M5 brane theory. And if you evaluate that thing for the case n equal 4, you get the formula I showed earlier. N being the number of particles. So for the D5 brane, the story is very similar. The significant difference is that we have 1-1 supersymmetry rather than 2-0. So the only change we have to make from the M5 brane theory is to replace the factor I20 with a factor I11, which has exactly the same structure, but here we have a 1-1 rather than a 2-0. And so it means that in the previous thing we had integrals d4 chi and there were no chi tildes. Now we have half of them are chi's and half are chi tildes. So these are the left chiral things and the right chiral things, because this is a chirally symmetric theory. And again, instead of having 8 delta functions for q's, we now have 4 for q's and 4 for q tildes. So the q's are left-handed and the q tildes are right-handed. But otherwise, it looks the same as the M5. I hope that's clear. So the Super-Yang-Mills theory is going to look much like the D5 theory because it's, again, involves vector multiplets. supermultiplets. So we have, again, the same I11 factor I just showed you appearing in the Yang-Mills theory. But now, instead of the dBi factor, we replace it by a Park-Taylor type factor, which has been discussed in previous lectures. It's this cyclically symmetric thing, but then you can replace 1 through n by some permutation, alpha, and then you have the alpha here, and then you multiply by the appropriate color-ordered trace. It's trace of matrix color factor, and sum over the inequivalent permutations, as usual. And so that's the answer for the super Yang-Mills, except it's not the full story, because the d5 theory I showed you only worked when only had non-zero amplitudes when n, the number of particles, was even. But the Yang-Mills theory certainly has interactions with an odd number of particles. So this isn't the complete answer. It's only the answer when n is even. So this raises the question, what is the amplitude when n is odd? And that is a non-trivial challenge to figure that out. And it's a little bit more complicated than the even case. But there's a nice way to answer the question. So the structure we're going to have is going to be very similar. We're going to have a CHY measure, a Park-Taylor factor, but then we have an I with a hat on it. And the I with a hat on it looks just like, we just put hats on the things we had before, and then we have to define what the hats mean. And the way we're going to answer that question is by starting with one additional gluon, gluon is a good word, in the amplitude, and consider a soft gluon limit to get the amplitude with 1 fewer particles. So we'll start with 2m plus 2 particles, take one of them to be a gluon, take that gluon to go to vanishing momentum, and then from that we can use standard formulas to read off the amplitude with the odd number of particles. So that's what we did. Now when you do this, what happens is that this extra particle gave an extra puncture on the worldsheet. So there's another sigma coordinate comes into the story, which we call sigma star. And there's this vector which is going to go to 0, but it appears in the numerator and the denominator with equal powers, so it doesn't disappear when you send p to 0, because its scale doesn't matter. So it survives in the formula that you end up with, but you can argue that the value of the amplitude doesn't depend on the choice. But you can't set it to 0 because you'll be left with 0 over 0. So that's a little tricky. So anyway, in this way, we got formulas. And I didn't write down the formula, but I sort of indicated it's going to look like the formula with one additional particle with coordinates sigma star and p star. So it looks like an even amplitude with those extra things, basically. Now, we wanted to be sure that we didn't make any mistakes in this procedure, so we checked all the symmetries, dimensions, delta functions, that they were correct. We saw that in the special case of n equal 3, their formula was worked out along about 10 years ago or more, or less, by these people, Denon et al. And our formula agrees with them. And they, in fact, had an auxiliary null vector in the numerator and the denominator of that formula. So that could have been anticipated just based on their work. It's okay. So you have something dot p star in the numerator and something else dot p star in the denominator, and the p star is null, and it's all set up such a way that it doesn't matter which null vector it is, and it gives the right answer. So they had already discovered this 10 years earlier for the three-point case, and we've just generalized it to all. It's a peculiarity of the spinor helicity formalism. As you know, if you just write a 3-gluon amplitude using standard polarization vectors, it's a very simple thing. You know how to do that. And it doesn't have that weird feature. But this is the same thing translated into the spinor helicity formalism. Oh, you do complexification. So these, yeah, you have to complexify to make this make sense. Yeah. Tree level. I don't know if it's manifest. It's true. Yeah, it can be proved, and I don't claim you can see it in your head, but it's true. Yeah, yeah. So we additional checks. Colin Cow is who was my collaborator on this. Is fantastic. You give him some horrible formula like this, and he checks it numerically on the computer. I have absolutely no idea how he does it. You can ask him. Anyway, he assures me that it checks numerically for n equal 5 and n equals 7. And the other thing you can do is you can consider the soft gluon limit of the odd n amplitude and verify it gives you the even n amplitude back. And that's been done as well. So for all these reasons, we're confident that the formulas are correct.
Can one also write an analysis formula for the non-abelian DDI?
The short answer is no. And the long answer we can discuss later. Okay. So, all right. So now we turn to the supergravity. Well, we've got all the ingredients we need, and you just have to assemble them. So for an even number of particles, this is the answer. I've defined all of these things already. And for an odd number of particles, this is the answer, and I've defined all of these things already, and that's it. And again, you can check that these are related by soft graviton theorems. You do a soft graviton limit on this, and you get this. You do a soft graviton limit on this, and you get this. So all that works. So the last theory we discussed in our third paper is the effective field theory that corresponds to type 2b superstring theory compactified on K3. And so that consists of a 2-0 supergravity coupled to 21 tensor multiplets. That's the unique number for which this theory is anomaly free. So in the string theory, this is the moduli space. Now we're just dealing with a field theory limit, so the field theory doesn't know about this thing, but it still knows about this. And so this theory has 105 scalar particles, right? Because there are 5 of them in each of the tensor multiplets. Now, if you're talking about the string theory, at fixed points of this duality group, the string theory would give you strongly coupled 2-0 CFTs, where these abelian multiplets somehow weirdly combine into these non-perturbative theories. So obviously we can't say anything about those, so we just stay away. Everything's okay if you stay away from those points. And then there's a perturbative effective field theory, at least at tree level. Just as an aside, this theory can also be obtained as a strong coupling limit of a heterotic string toroidally compactified to 5 dimensions. When you toroidally compactify the heterotic string to 5 dimensions, there's a dual interpretation of that 5-dimensional dilaton as the radius of a 6th dimension. So you go to strong coupling of that, and it gives you exactly this same 6-dimensional theory. Pardon? Yes, but in the strong coupling limit, it's no. The 5-dimensional. You see, it's got this extra circle, and you decompact if you think of going in the other direction. If I put my 6-dimensional theory on a circle, and do dimensional reduction, I'm going to get a non-chiral theory. Okay, so this is just the same statement in the other direction. Okay, and here, using soft theorems, we can verify that, in fact, the scalars parameterize this moduli space. And that was done as well. So I'll just mention a couple other things we did, but I won't go into any detail on. We can get the maximal super Yang-Mills and supergravity amplitudes in 5 dimensions, tree amplitudes, of course, by straightforward restriction of the 6-dimensional formulas to 5 dimensions. When we go down to 4 dimensions, you can do something a little less trivial. It is possible to go to, in the spinor helicity formalism, it's possible to go down to 4 dimensions from massless 6 dimensions to a theory in 4 dimensions that has masses. So you can land on the Coulomb branch of n equal 4 4-dimensional super Yang-Mills. So we can get amplitudes for that as well by reduction from these 6-dimensional theories. So in conclusion, we've obtained tree amplitudes for various supersymmetric theories in 6 dimensions for M5, D5, 1,1 the Yang-Mills, 2,2 supergravity, 2,0 supergravity with 21 tensor multiplets. Now the final 3 theories here each are known to have UV completions as string theories. In the case of the super Yang-Mills, the UV completion of this would be little string theory. And then these would have completions. This one, as I said, by putting as 2b on K3, and this one just as 2b on a torus. And so even though we've only talked about tree amplitudes, it's nice to know that there is a quantum theory behind this. In the case of the M5 brane and the D5 brane, there may be a quantum theory behind it as well, but I think you would have to bring into the play the gravity multiplets gravity associated with the space in which these branes live. So it would involve adding additional massless degrees of freedom. So it wouldn't be quite as straightforward as in the other 3 cases. Now there's obviously other things one could do. One could try to extend this analysis to theories with 1,0 supersymmetry, and there's a vast landscape of such theories, which has been explored mostly by people who work on F theory, and would be interesting. Personally, I'm more interested in trying to go up in dimensions, say to 10 or 11. And spinor helicity formalism in these higher dimensions gets a little trickier. But I think if one tries hard enough, it should be possible to do something. And we saw this morning from Conca that he even without a full control of the spinor helicity formalism in 10 dimensions, he had enough control that he could give us some very interesting results that he reported. So I guess I'll stop there. I don't know. We haven't thought about it. I mean, we're aware of the question, but we haven't thought about how. We haven't tried, is maybe a better way of saying it. We haven't tried to do that.
I mean, it's presumably related to the difficulty with the non-abelian point clock, because in that case, there may not be a canonical theory.
Yeah. So in the non-abelian Born-Infeld, as I hinted, I have some strong feelings on it as to why there are obstacles. These theories that have UV completions, I would like to construct them and show them to you, but it hasn't been done. So I'm hoping that could be done, as that's a possible project. But I'm a little more motivated to go up in dimension rather than up in dimension of the operators. Can we do massive in 6 dimensions? Well, that would be harder. So I mentioned how we can do massive in 4 dimensions, starting from massless in 6 dimensions. Once and if we sort out massless in 10 dimensions, perhaps there'll be an analogous way of going down to 6, which brings in mass. But that hasn't been achieved yet, to my knowledge. Certainly we haven't achieved that yet. I can't swear that nobody else has. So we have not, in our deliberations, discussed worldsheet theories that would be responsible for these formulas. Now, of course, we're very much aware of the work of Lionel and his collaborators on ambitwister string constructions, where they have successfully confirmed some of our results and made proposals for results even in 10 and 11 dimensions, which I must say I don't fully understand, but look very interesting. So that's all I could say about that. Checked all the what? Recursion relations. I haven't. Have you?